In this video, I'm going to talk about vector algebra. So this is going to be basically about the algebra of vectors. So you know that when it comes to the algebra of mathematics, we have to deal with the multiplication, we have to deal with division, and we have to deal with the subtraction and addition. So these are kind of operations. Actually, these are kind of basic operations in the algebra, in the mathematics. So but when it comes to the vector algebra, it is somewhat different from the mathematics that we know, that we used in day-to-day life. So in this video we are going to look how vector algebra is done, because when it comes to vector algebra, it has different meanings and different notations to add and to subtract. So we have to know about them when we study the vectors, when we are analyzing the vectors. Okay, in here I have taken two vectors of a and b. So I can write this in terms of x hat and y hat and z hat. So these are the unit vectors along x, y, z directions. X, y, z. Actually, this is a Cartesian coordinate system. So we in this Cartesian coordinate system, x hat, y hat, and z hat are the unit vectors along x, y, z directions. So now I can write the a vector in terms of x hat, y hat, and z hat. So now this ax is the component of along x hat direction, and the ay is the component y hat direction, in the y hat direction, and the az is the component of z hat direction. Similarly, I can write this for b vector as well. So bx is the component along x hat direction, and by is the component along y hat direction, and bz is the vector component along z hat direction. Okay, now first we are going to look at the vector addition. So in here we considered only two vectors, a and b. So a plus b, the vector of a plus the vector of b. So we're going to derive an expression for this a plus b vectors. So now you know that the component along x hat direction is the ax and the bx. So these components added together, and ax plus bx is going to be the vector component along x hat direction, and likewise ay plus by is the component along y hat direction, and the in the z hat direction, az plus bz is going to be the vector component along z hat direction. So this kind of expression we can derive for the vector addition of two vectors. When we have two vectors, we can add them together. So this kind of expression can be obtained when we add two vectors together. Okay, now I'm going to subtract two vectors. We have a and b vectors, so we are going to subtract b vector from the a vector. So we will have ax minus bx. This is the component along x hat direction. Now we have ay minus by. This is the vector component along y hat direction, and this is the az plus az minus bz is the component along z hat direction. This kind of expression can be obtained for the vector subtraction. Actually, we have these two vectors actually. So when we have two vectors, if we are going to subtract them, so we will have this kind of expression. Okay, next I'm going to derive an expression for the scalar product of two vectors. I have taken a and b as my two vectors. So from the from the beginning. From the beginning, I have mentioned that the a and b, what are those vectors? Ax plus x hat plus b y hat, and a z hat is the a vector, and b likewise we have a expression for the b vector as well. So, and when we are going to get the scalar product of these two vectors, so first I'm going to write the a vector ax x hat, ay y hat plus az z hat. This is the dot product actually. So when you are considering scalar product, you have to get the dot product. So this is also called as the dot product as well. So now we have this b vector bx x hat and by y hat and bz c hat. So now I'm going to get the dot product of these two vectors. So now I'm going to expand this. So now we have ax bx x hat dot x hat. So x hat dot x hat, what does it mean? So actually, what is the value of this? Actually, we have x hat dot x hat. So this is a scalar product of two unit vectors. Actually, when we have I'm going to show you actually. So when we have this Cartesian coordinate system, this is z direction, this is y direction, and this is x direction. So we had this x hat direction along the x direction. So what we have is that x hat is also parallel to the x hat other x hat vector. For an example, if you take another x hat unit vector like this, so the angle between these two vectors will be 0 because these two are parallel to each other. So now I'm going to go through with the definition. So what does it mean? The definition: x hat magnitude, magnitude of x hat times the cosine of the angle between these two vectors. The angle between the two vectors is 0. So we have cos 0. So for a unit vector, we know that the magnitude of a unit vector is also 1, and we have this 1 here, and cosine 0, you know that it is equals to 1. So we have 1 here. So x hat dot x hat is going to be equals to 1. So likewise, you can say that y dot y is y dot y hat is equals to 1, and z hat dot z hat is equals to 1. So when we expand this, we will have ax times by, actually we have ax y by x hat dot y hat. So what will happen to this? What is the value of this scalar product between x hat and y hat vectors? Actually, these are unit vectors. So I'm going to consider this x hat dot y hat. So we know that x hat, from the definition, we know that x hat magnitude, y hat magnitude times cosine the angle between these two vectors. And so the angle between these two vectors, actually we have x hat direction along x direction, so we have y hat along y direction. So angle between these two x hat and y hat will be 90 degrees. So that means we have to consider cosine 90. So cosine 90 means that the magnitude of x hat is equals 1 and magnitude of x y hat is equals 1 and cosine 90. So what is the value of cosine 90? Cosine 90's value is 0. So we have x dot y dot y hat, x hat dot y hat is equals to 0. So this means that we will have ax x hat dot bz z hat. So bz z hat. So we will have we will have few actually. I think it's gonna be 6 or something like that. I'm not going to expand this equation, so expand this expression actually. So we will have terms like x hat dot y hat, and we will have y hat dot z hat. So likewise, we will have this kind of similar dot products. So these are going to be 0. Only the x hat dot x hat and y dot y hat dot y hat and z hat dot z hat is equals to 1. So when we have a dot b dot a dot b, we will have ax bx and ay by, because the x hat dot y hat is equals to 0, these terms are going to be cancelled out. So and only we have x hat dot x hat, it is equals to 1. So we will have 1 here and we will have 1 here. So we will have az bz term. So these are going to be the value of a dot b. Okay, now I'm going to derive an expression for the cross product. So we have this a cross b. Actually, sometimes you can write this as a cross b in this way, but I'm considering this a cross b. So these have similar meanings actually. So what I'm going to do here is that I'm going to put this into the matrix format. So we have x hat, y hat and z hat in the top of this matrix, and we have this coefficients of x hat and y hat and z hat for the a vector. So we will have a vector here. So we have ax, ay and az. So in the bottom of this matrix, we will have to write the coefficients of x hat and y hat and z hat of the b vector. So that is bx, by and bc. So right now we can derive an expression for this matrix. Actually, this is the determinant of this matrix. By calculating the determinant of this matrix, we have a expression for the a cross b, that is the cross product of two vectors. So I'm going to do this for you. First we have to write x hat. So we will have to multiply ay bz and subtract az by. So ay bz and minus az by. Likewise you will have y hat. So if you are considering this as plus, so you will have to consider this as minus, and you will have to consider this as plus. So that is why I put a minus sign over here. So if you take the y hat here, so you will have to forget about this column and you will have to forget about this row. So what you have, the determinant is ax bs bz minus az bx, ax bz minus az bx. So now we have this z hat here. This is a plus sign. There is a plus sign, that is why I put a plus sign here. So z hat means that you have to forget this column and you have to forget this row. So right now we have ax by and ay bx. So ax by minus ay bx. So this is going to be the value for the a cross b. In the previous video I have mentioned that when we have this cross product between two vectors, so you will have a vector. So I have taken an example in the previous video. So this is actually a general expression for the a cross b. So I hope you all understand about the vector algebra that I taught here. So in the next video, I'm going to talk about the triple product of vectors and scalars. Because when we are considering triple product, we have a scalar product as well, we have a scalar product and a vector product as well. So see you all in the next video.